Hi everyone, we're going to continue our discussion on structure by talking about a little more detail about the orbitals that are involved in bonding. So the general way, very watered down way we think about bonding is we have atoms that they have a certain attraction to each other, but they also have a certain repulsion to each other because of the negative and positive charges and because they want to fill their shells, but they don't want to get too close because they start repelling like charges. So as these come together, there's a certain amount of attraction that brings them together. But then if they get too close, there's a repulsion that takes them apart. So there's an ideal length or distance between the two of these that balances those attractive and repulsive forces. So in this diagram here, it's showing that the attractive forces are very good, and then the repulsive forces are not so good. So that part where there's a lowest potential energy due to these two being a certain distance from each other, that is the ideal distance that is what we consider the bond length. One way to think about this is that you have remember electrons are not just particles but also waves, the wave-particle duality. Those waves can overlap with each other, and they can be a positive interaction or constructive interference where the two waves are in phase and they sum up in a sense to a larger wave. Okay, so that's sort of a bonding interaction or a good way of the two waves interacting with each other. You can also have destructive interference where the two waves don't add together, they cancel each other out to some degree. So that's called destructive interference. We're mainly going to be thinking about constructive interference and that the places where the overlap occurs between the electron clouds, that is sort of how we think of the covalent bond, not like a stick, but these clouds or electron waves adding together. But let's actually review where are those electrons. So in a carbon atom, for example, you have the 1s2 electrons, 2s2, and 2p2. Okay, so you have 6 valence electrons for carbon. Its atomic number is 6. Now, if I look at this diagram, and remember we were talking about unpaired electrons pair to make bonds. How many bonds would you expect for carbon just based on its valence shell? Well, there's 2 unpaired electrons, so you would think that carbon would just pair those and it would make 2 bonds. Now, we know a couple things about carbon already. We know carbon actually makes 4 bonds, and so we usually have carbon with 4 bonds. And then we also know that usually, like in methane, CH4, we know that all of these bonds are equivalent to each other. That means they all have the same energy. It takes the same amount of energy to break this bond, called the bond dissociation energy. So you've got equivalent bonds, and so it's not like you have 2 different energies due to the s electrons and the p electrons. They're actually in the same energy orbitals. So how do we explain that? One way to explain that is hybridization. Okay, so for example, I'm going to show you what we do with this. Instead of 2 unpaired electrons, I want to use the idea that there's 4 bonds, so I need 4 unpaired electrons. To get 4 unpaired electrons, I'm going to mix these orbitals together, and I'm going to have 4 orbitals that are the same energy, because remember these are all same energy, and I'm going to distribute the electrons so there are 4 unpaired electrons. So I'm going to take these 2 core electrons down here, just stay there, and then the valence shell up here, I'm going to have 1, 2, 3, 4. Which electrons are responsible for bonding? We emphasize that it's the valence electrons. The outermost shell is available for bonding interactions. When these atomic orbitals are combined, we filled in the hybrid orbitals. The hybrid orbitals, there's conservation. If I have 1, 2, 3, 4 atomic orbitals, I can create 1, 2, 3, 4 hybrid orbitals. Okay, so now hybrid orbitals imply we're talking about molecules now. These are the orbitals in a molecule. Okay, so we're going to use those orbitals. Hybrid orbitals are created from All right, now the ones that we're talking about are created from one s orbital and 3 p orbitals. So 4 total atomic orbitals. And they're called sp3 because it's 1s and 3p. So s1p3 or sp3. And how many of them are created is conservation. It's the same number. Is the potential energy the same or different? So potential energy is this. S orbitals are lower than their corresponding p orbitals, but when you mix them together and you redistribute them, they're going to be equal now. And notice the energy is somewhere in between the s and the p. So they're not the same energy as either s or p. One s orbital with 2 p orbitals, if you only mix these two, one s orbital with 2 p orbitals, now you no longer have sp3 orbitals. You would have sp2 orbitals. So that would be sp2. And then s and a p, and you mix those together, you get sp orbitals. Now let's talk briefly about how many you would get. Coming back to here, one s orbital and 2 p orbitals is how many atomic orbitals? 1, 2, 3. 3 atomic orbitals. How many sp2 orbitals will there be then? There will be 3 of them, right? So I'm going to put 3 sp2 orbitals will be created. If you have one s orbital and one p orbital and you mix them together, you actually get 2 sp orbitals because 2 go in and 2 have to come out. All right, so let's see if we can figure this out. Type of hybrid orbital, if we're talking about sp3, 1, 2, 3, 4 orbitals in and 1, 2, 3, 4 orbitals out. So here's 4 hybrid orbitals. If we do sp2, we're only mixing these 3 orbitals in and we would get 3 orbitals out. Now you might wonder, where's the extra orbital? This guy, okay? Remember, this one didn't get mixed with the others. So that one would be what we call an unhybridized p orbital. We just leave it. Okay, so remember p orbitals look like that. We just leave it. Okay, so that means for sp2, we would have 3 hybridized sp2 orbitals, just like here, I put 3. But we'd have 1 orbital left over. The 2p orbital would be left over. And now thinking about the sp orbitals, let's try that. sp means we're mixing these two together. How many unhybridized p orbitals would I have now? I would have this one and this one. I would have 2 unhybridized p orbitals and 2 sp orbitals. So I'd still have 4 things coming in and 4 things going out, but only 2 would be hybridized. And so I'd have 2 unhybridized p orbitals. Okay? So that's a lot of talking. Let me draw it out a little bit. Okay? So sp3, what that means is I put in an s and 3 p's, and I get 4 sp3 orbitals. For sp2, I put 1 s and 2 p, and I mix them together, and I get 3 identical sp2 orbitals. But then I have an unhybridized p left over. It's just like that. And then if I have an sp orbital, I have 2 of them because I'm mixing s and p, and I get sp and sp out. And then I'm going to have 2 unhybridized p orbitals. All right, so that's sort of what we're going to be aiming for. Now let's talk about the type of bonds. We have 2 kinds of bonds that we normally talk about. Normally when you see a single bond, it's what we call a sigma bond. Okay, so a sigma bond is when 2 electron clouds come together, and like you can see with these 2 hydrogen atoms, they come together and they have that constructive interference, so the waves that are in phase with each other adding together. And the head-to-head overlap is a certain kind of overlap that is very strong. I think of it like, you know, my hands clasping together, or like 2 trains connecting, 2 train cars connecting together. Okay, so that's a very strong overlap. So I want you to think about that. This is called a sigma interaction. Now a pi bond is formed from an side-to-side overlap. So it's not this so much as it's this, okay? And the way I think of that is like Velcro. Like you have two strips of Velcro and they're attracted to each other, but they can be pulled apart easily, right? So it's not as strong as a head-to-head overlap. Now these side-to-side overlaps tend to occur with the p orbitals because the p orbitals are lined up vertically and then they overlap with each other sideways. And sometimes the p orbitals can go this way and do a head-to-head as well. So just keep in mind that most of the time when we talk about the p orbitals, there's going to be some pi bonding between them. And two ways to draw it. Well, so here's some p orbitals, and there's overlap between them. And one way to think about the overlap is as like just sort of a shading across there. So these guys overlap to form one big orbital here and an orbital here down here. So you can see the regions where the overlap is. So combining it all together, here's an orbital picture. And it's a little bit hard to read. There's a lot of stuff going on there. First, we'd start with a really simple picture of what is the molecule we're talking about, usually represented as a Lewis structure. So here's what we call ethane. It's two carbons with a double bond and then hydrogens around it, C2H4. Now if you look at C2H4, one of these bonds is a sigma bond, and then when you see double or triple bond, those extra bonds are pi bonds. Over here, it's a single bond, so this is also a sigma bond, and this is a sigma bond. These are all sigma bonds. So what I'm seeing is I'm seeing 1, 2, 3, 4, 5 sigma bonds, and then this extra bond is a pi bond. Therefore, a double bond is not two sigma bonds, it's not two pi bonds. A double bond is a sigma bond and a pi bond. A triple bond is a sigma bond, a pi bond, and another pi bond. Okay, so keep that in mind. When we look at the diagram here, you're going to see that the sigma bond is right here. See the head-to-head overlap between the two carbons. Okay, you have sigma bonds over here. Again, head-to-head overlap between those electron clouds. And then the pi bond is from these unhybridized p orbitals. They're overlapping with each other in a side-to-side attraction. Okay. So, and keep in mind too, the pi bond, there's only one pi bond, right? See this guy right here? So this is not two separate pi bonds. It's an interaction because you have one lobe of the p orbital and another lobe down here. All of that is considered one pi bond. Let's review a little bit again about the sp3. The number of hybrid orbitals, when you have sp3 orbitals, there are 4 of them. Okay, so that means there's nothing left over to have p orbitals. They've all been hybridized into sp3. So when we look at when we look at the number of sigma bonds, that is usually due to the number of hybridized orbitals. So if we look at 4 sp3 orbitals, that means that there's 4 hybridized orbitals. Then they're usually going to make 4 sigma bonds with those orbitals. All right. Then the number of pi bonds is usually due to the p orbitals that are present, but they've all been hybridized in this case. So I'm not going to have any pi bonds usually when I'm talking about an atom that has sp3 orbitals. They're all sp3. There aren't any p orbitals to do the side-to-side pi bonding with. Okay, let's see if you can fill out the rest of this. All right, so if you follow that pattern, you'll see this is the way that we filled it out. So this is just a way to remind you of, well, to look at the patterns and to figure out what you would expect for bonding. When you look down here at the next problem and you see pi electrons, well, is that where do those pi bonds come from? You know, they come from those unhybridized p orbitals. So you're not going to have sp3, you're going to have either sp2 or sp, okay? Now in this problem, we'll do an example together. The idea is that you want to try to look at a central atom and you want to determine what is the hybridization of that atom, meaning what are the hybrid orbitals it might be using to bond to its nearby atoms. So in this case, what I would do is first label sigma or pi. Think of sigma as single bonds. So I've got sigma, sigma, sigma. From there, I want to look at how many sigma bonds, how many sigma bonds there are, 3. So that's likely to be 3 sp2 orbitals. So these are sp2, sp2, sp2. Okay, so that means there's an unhybridized p orbital potentially in there. All right, so keep that in mind for later. But for now, we can just say, oh, that guy is sp2. All right, guys, let's look at your answers here. So I've got these answers here. Feel free to pause it, check your answers. Now let's talk about this one because the lone pair throws people off. Think of the lone pair as the potential to form a sigma bond. So that means you can treat it like a sigma bond. So you've got 1, 2, 3, 4 potential areas. So this is going to be sp3 hybridized, where one of the orbitals is going to have a lone pair instead of overlap to make a bond.